So thank you, Mushin. I was supposed to start with some inspiring music again, but you can sing it in your head, like "Here comes the sun," because of this nice Florida weather. Okay, so spin-foam dynamics. Here we go into the matter, and let me remind you where we were yesterday. We were discussing the fact that what we wanted to discuss are processes, like in the spirit of what we do in quantum field theory. So we have in and out states, and we compute the probability for going from one state to another. And usually in quantum field theory, we do this using a path integral, Feynman path integral, that we write in terms of Feynman diagrams and so on. So we wanted to do something similar here, except that now the process that we are going to describe is space-time itself, and we have to respect the symmetry of space-time. So that's why we call this approach covariant. So we have to make, we said, we need to make sense of this path integral here that there is in the right corner of the slide. It's a formal path integral at this point, but we have already understood that this path integral represents a sum, well, an integral over histories. But now the history are a history of space-time itself. Well, actually, history of space that evolves, making up space-time. Okay, we introduced yesterday some technologies to write concretely this object, and importantly, so this is an integral over histories that, because of the fact that we are working with the truncation of the theory, becomes a sum over histories. So here you see that the amplitude is defined as a superposition of all these histories, okay? This is what is expressed by this sum over sigma, where sigma are the histories. And a single history is what we call a spin-foam. You will see in a moment how it comes to be. And then in the spirit, so what is a spin-foam? Is this thing in which I do basically the same thing that we have in usual quantum field theory. Like I said, we have some quanta that evolve, they go through some interactions, so they can transform in some other quanta. And this corresponds, my quanta here are represented by spin network states, the quantum states of the geometry. So what I want is an evolution of these spin network states through an interaction represented by a vertex. So the structure that you see here is similar to what you have when you write down the Feynman path integral, that are a way to picture all the different elements that comes into the description of a quantum process. And here we have the same thing, and we will really do the same in the sense that for each element that we draw, we also associate a piece, a mathematical element in our computation. So let me tell you just one more thing. Of course, so this is an evolution of a three-dimensional geometry into this four-dimensional space-time. So what's inside that belly, in the bulk of my computation, in this region of space-time, is a four-dimensional geometry. It will be similar to what we have done before, so I can describe this in terms of simple geometrical elements like links, nodes, edges, faces, and so on. So this object that I have here mathematically is called a two-complex, or simplex here. So you have to imagine, for instance, if you have let's do this in one dimension less. So if you wanted to construct an object in 3 dimensions, a simple object in 3 dimensions starting from a 2-dimensional object. So the simplest geometrical form in 2 dimensions is a triangle. And to construct a tetrahedra, a polyhedra, so you pick up a point out of your triangle in the outer space, in the extra dimension. So, and then you connect all the vertex of your triangle, and you form a tetrahedra. So here you have to imagine that you are doing the same. You pick up a tetrahedra, you put a point in your extra dimension, your 4th dimension, and then you connect everything. And so this is the kind of geometrical objects that we have to picture in our mind. Of course, it's difficult because it's 1 dimension more than what we picture in our head, but this is the idea. Then you can figure this in your hand by performing projections, right? Okay, so we have this kind of thing, and we can give names to these objects. So I started with a spin network in which I have a node and links, and I wanted to look at the evolution of the spin networks. So if I take a node and I evolve it, I get something that is like a line, but it's a different line than the one I have in the boundary because it's a line that's, say, in the bulk. So let me differentiate this kind of lines. The lines that is an evolution of a node, I call it edge, okay? And then if I evolve one of the link in my boundary spin network, I have this link is spanning a surface. So I call this a face, okay? And then where things happen, where I have a change, where I have an interaction, I have a point, but this point is like a fat point in the sense that it's different than the nodes in the boundary. This is what we call a vertex. It's really our interaction vertex in the theory, okay? So these are the names, and I hope this will bring no further confusion. And of course, you see that the kind of thing you have in the bulk, now it's really something like a form. So, hence, it's a form in which we will have representations of SU2 and SL2C. So we have spins, and hence, here there is the famous spin form, okay? So let's try to understand how to go from this bubbly space-time to something that gives a concrete computation. And let me mention, of course, these computations have been figured out for the first time some 15 years ago. Of course, Jonathan Engel, Pereira, Rovelli, Levin, and then the PI people, Laurent Friedel, Krasnov, and then the Polish group, Kamiński, Kieslowski, Lewandowski, and then many, many other people. So, how do we compute things with these objects? Let's try to understand better. Sorry. What's going on here? So we have, in the previous slide, you saw that we have superpositions of histories, so superpositions of spin forms. So let's focus on one particular spin form. And this spin form could be constituted with one vertex, or 2 vertices, or 3 vertices, and so on. So, in fact, I can have an expansion in the vertices, exactly like you do with Feynman diagrams, okay? In which you expand your theory. First, you compute 1 vertex, 2 vertex, and so on. So I wanted to do the same, and the idea is that if I compute the single vertex, this will be the dominant contributions to the amplitude, and then all the other contributions will give corrections. This is not yet a theorem, but there are many indications that this is working in the theory. So the point is that we want the basic object is just to compute the amplitude associated with a single vertex. That's what we want to compute. So let's focus on a single vertex in my theory. And so the spin-form can be more complicated than the one that is pictured in this drawing. But imagine that in a big spin network, you focus on one vertex. And then how do you do this? You basically cut a finite region of space-time around your vertex, okay? So you have the vertex in your big space-time, in your big region, and imagine like you can really do a cutting all around, so then you focus on just a finite region around the vertex. So then, again, what you are doing is to single out the boundary of this region. That means that there will be some boundary spin networks that I call like the vertex boundary spin, the vertex spin network, because this is just the spin network, just the states that is associated to that particular vertex, okay? And then we use the technology that we have introduced yesterday. So yesterday we understood that the main tool, the magic tool that allows us to define the dynamics is this object that is the simplicity constraint. And the simplicity constraint is also embodied in a map that is called the Y map. And this map connects representations of SU2 into representations of SL2C. So now I have my, so you see here in this equation, so this is the expression of my vertex amplitude, okay? So this seems, yeah, I have, this is the expression of the vertex amplitude, okay? And it's very compact. I write it here, and it's very powerful. So let's learn how to read it and how to do computations with this. So you write down concretely a spin network that is on the boundary of your vertex, okay? Is this object here. And then you want to connect it, you want to map it into a state that is a SL2C state, like we did yesterday. So the Y map acts on this state and gives me a SL2C states. Good? Then we said SL2C states are much bigger than the physical states of my theory because I want those that are also invariant by Lorentz transformation. So as we did for the spin networks, I wanted to take a quotient over selecting the subspace in my Hilbert space that corresponds to gauge invariant states. And I do this using this object. That will be just the standard way in which you take the gauge invariant part of your theory, that is by doing a group averaging. So we will write this explicitly in a moment. So you have SU2 spin networks that are taken into SL2C spin networks, and then these SL2C spin networks are projected into the invariant subspace, okay? This is what this expression is telling you. And then I have to extract a number, and to extract a number, so of course this is will be a function of some group elements, like we did yesterday. So you just want to evaluate for a choice of group element. So a simple choice is to take evaluation of the identity. I run this algorithm and I get out a number, and the magic is that the numbers that you get out by this simple procedure are exactly the same numbers that in the classical limit you get when you compute things with the rejection. Yes?
Sorry, I'm a bit lost in the in this slide. So isn't that we define the state on the boundary as the spin network state?
So in the bulk, so the bulk is where you have the Lorentz group, of course. So the point is that what you are doing is to pick up a finite region inside your bulk, okay? And then, because you are picking up this finite region, on the boundary, you have, again, an SU2 states, and SU2 spin networks. Then, so what happens is that if you want, so this is a pictorial representation, so possibly, so we will see in a moment more precisely. Sometimes your boundary spin networks around the vertex can extend and become actually the true spin network on the boundary. It depends. So cases could be complicated, or like in this case, the spin network you see around the vertex is indeed exactly the same as the one that you have in the actual boundary of your full space-time region. But so this is a general procedure when you can have many, many vertices. And yeah, so to say again, the answer is yes to your question. Yes, you pick up just an SU2 spin network.
So yeah, but isn't that this vertex leaf in the bulk? So isn't that, it means that this vertex is supposed to be the state in the SL2C? And
but that's exactly what we do. With all this procedure, we see how to make things, how to get a state in SL2C, but starting from an SU2 state. Good.
So this psi knew
sorry, in the end of this procedure, you have something, an object that is an SL2C one. Yeah.
Just to make sure one more time, so that psi vertex that you have in the expressions, is that the state in the SL2C or the state in the SU2?
The psi V is an SU2 state.
Ah, okay.
Good.
Yeah.
I will add some more. Informations in the moment. We will write down this explicitly. I just wanted to give you the picture of what's going on, but we will see in this in a moment. So yes, let's see this more precisely. Okay, so now you here we are. Here we see things. Oh, before I go ahead with this, any further question? Yeah.
I have a question regarding the notion of causality in spin forms, because we've seen the simplicity constraint imposed yesterday, and it seems to me that in the simplicity constraint there's no a clear notion of causal evolution. Oh. We want to understand that, right? It's in the sense of computing the vertex, the amplitude, transition amplitude between one state and the other state. Would you say that is a feature of the spin form? Is that notion correct or not?
Let me see if I hope I understand your question, because causality means many different things. And we have a notion of causality that has to do with the fact that here we have a Lorentzian spacetime. So in this sense, causality in that particular sense, in the sense of light cones and so on, it's well defined, of course. Even though we have superpositions of histories, so it will be also superpositions of causal structures, okay? But I don't think this is what you meant, because I think you have in your head like a directionality. And the point is that general relativity doesn't have a time direction in the sense of a arrow of time, because the arrow of time comes with thermodynamics. So it's a good feature of this theory that I can run the amplitudes going from an in state into an out state, but I'm not saying, so I'm sorry, it's difficult to say these things without putting some language of our experience into it. But so I can exchange the out state into the in state and vice versa, and the amplitude gives me the same probability. Exactly in the same way in which the equation of motions in general relativity, I can look at them in one time direction, or I can take the time reversed. If I wanted to have an arrow of time, like always in physics, you have to insert some thermodynamical considerations that we can do. Yeah.
Thank you.
Good? Okay. So let's try to understand better. So let's try to look a bit more into the details of this construction, put in some more informations. And let me say also that this is a very general way to write this object, and I have already highlighted yesterday the fact that then you can write it in many different ways. So this is the core of the story, and then concretely how you perform all these operations and how you factorize all the different elements in the expression that you write down, well, it's a matter of the research that you may want to do, because it amounts to find smart ways to do the computations. So I will give you a version of this here. So we have to work first, remind things from representation theories, and the representation of SL2C are complicated, but we can draw from the information that we have of SU2 representations, and we will see the similarities between what we have in SU2 and what we have in SL2C. So we use SU2 representations, and concretely the objects that of the representation are called the Wigner matrices, that are this D, represented with D. They are matrices, so the matrix elements are indicated with this M and N, and these representations are labeled by a number that is called the spin. So these objects that I write here, the D, the Wigner matrices, are complicated. They are written in terms of sine, cosine, but basically what they do, they are rotations, right? But they are complicated, but we know precisely their expression. And also, if you wanted to do things on a computer, for instance, you can open your notebook in Mathematica, and the Wigner matrices are already written there, so you have just to call them. So doing calculations with them, it's easy. So what these matrices are doing is, so when I take one of those, they are, so like in this sandwich here in which I have an element of SU2, so here I am picking up one matrix element, one particular element in these transformations. So what about SL2C? Well, with a bit of abuse of language, we can extend the original matrices defined by Wigner to Wigner matrices for SL2C. And we saw yesterday that the representations of SL2C are such that instead of having just, instead of being labeled by just one number, they are labeled by two numbers. So here my representations, my Wegener matrix is now carrying two numbers, and I have the corresponding, and I have then my magnetic numbers that are written in the bottom. So I can act with these matrices on states that are SL2C states, like the one we need for writing down our amplitudes. And we know, we have the Peter-Wald theorem that tells us that now we can decompose our Hilbert space. That is, we have seen this for SU2, that we can decompose it in Hilbert spaces for of states that are valued in SU2. So the decomposition gives me a direct sum over all the different representations. And I can do exactly the same in the case of states and Hilbert spaces in SL2C, okay? And then I can define the Y map, and what I'm writing here is the Y map, but written in the group basis, okay? So this is explicitly, we can translate the expression that we had before into a concrete computation. So now you can take this expression and you have just to call in your mathematical notebook the Wegener matrix for this and the Wegener matrix for that. And you see that I can define this object P here in this way. So what about now my vertex amplitude? For every link around the vertex, the Y map is transforming this into an element of SL2C. And then P projects on the invariant part of SL2C, and this is obtained by performing a group averaging at each node of this spin network. Now, and then, of course, the next step is to evaluate everything on the identity. That means that you take your group element G equal to 1, basically. So, concretely, so here I have a single vertex, but you can imagine that you can have other vertices, and you can perform this game of defining the boundary spin networks for each of these vertices. So the total and again, in the spirit of what you would do with the Feynman diagrams, here you really associate to each link, you associate a group element H, and to the edges you associate this group element G, and so on. So the H are group elements in SU2, and the G here are group elements in SL2C. I group average over all of them, even though, of course, because I evaluate everything on the identity, then the G they disappear. And careful that, if I have a very complicated spin network, I will do this for everything that is in the bulk, but not for what is in the boundary, in the real final boundary. So the final expression will end up to be a function of the boundary states. So you see that, so this is something you will see very clearly also in the numerical computations. So Hongwang will probably go through this. So when you compute a spin network, basically what you need to do is to give the boundary data, and the final result, your final number that you extract from this computation will be a function of this boundary data. So, so this is what is expressed here. And so, as I said before, defining so you have this expression, and then so the final expression here, it's an amplitude that is the amplitude for the full two complex, that is the geometrical object that you have in the bulk. That is a function of the boundary data, and can be written in this simple way, connecting all the different group elements, taking basically a delta here so that they are connected. So we saw basically that we have all the ingredients to put this on a computer and compute it, but if you do this naively, basically your computer will give you back nothing. So a lot of the work that goes on into defining these amplitudes is about how can I find approximations or factorizations that allows us to extract numbers in a reliable and quick way. And I think something that is underappreciated is the fact that in this work, so it's not just about doing coding, but it's a interplay between analytical work and numerical work. So on one hand, you want to make your codes more and more performing, but it makes no sense to do this in a hard manner unless you work on the analytical side, trying to adapt the expression of your amplitude to the particular code that you're using, or maybe also to the particular problem. So there could be situations like doing computations for cosmology of black holes, in which you may have some simplifications like usual, like you may have some symmetries that allow you to simplify these objects. And so you may want to exploit this. So here in this, I am in particular flashing a version, a possible writing of the transition amplitude that was found a few years ago by Simone Speziale. And this is what has been used a lot in the computations, in particular in this SL2C form next. And so this is a library that is publicly available. So I encourage you to go download it, install everything, and try to play with this. And as I said, so this particular library exploit this form of the spin form, where you can see now the amplitude is written in terms of a 15J symbol. A 15J symbol is a generalization of the Clebsch-Gordon coefficients. Clebsch-Gordon coefficients are the objects that allow you to sum some spins. So here in my computations, I have to put together 15 spins in a gauge invariant manner. So this object does this for you. And so this is all in SU2. And then you see the factorization is such that I put all the information of the boost in this boost factor. This is just an example of the kind of things you can do. And I forgot to add here that there is a very nice review of these techniques, these numerical techniques, written by Pietro Donà and Pietro Paolo Frisoni. And this is a bit complementary to what you will see later in the presentation by Hong Wang. So I think that most of the things that Hong Wang will present will deal with numerics for very large spin. And if instead you want to deal with small spins, you may want to use this. So again, our job is to find the right tool for different problems. So what can you do with these amplitudes? Well, you can do a lot of things. You can compute endpoint functions. You can compute black to white transitions. You can compute contracting universe that goes into expanding universes. And you can use different numerical techniques, including, for instance, try to compute things using Monte Carlo methods, using saddle points methods, and so on. And what I will try to convey in my next lecture is the fact that you don't have necessarily to go into all these computations, but you can also extract some very simple and powerful information just by some basic properties of the amplitudes, for instance, the simplicity constraint. Any question at this point? Yes.
I just want to go back a little bit to the
to
the first question I had. This might be a naive question, but regarding the probability amplitude that you mentioned before, are there any subtleties in the interpretation of this number? Like at the end, we compute this amplitude, the transition amplitude. This gives a number, right? What this number means? What is giving us? What is telling us? And in the context of what you mentioned before, since this is a sum over stories, a sum over different causal stories, this seems like the path integral is like a projection over, like a projector over the simplicity constraints, or it's a projector over the constraints that we impose in order to recover general relativity, right? So that seems slightly different from the path integral that we have in QFT, where the path integral is interpreted as a causal evolution from one state or the other, in the sense of unitarity and all of that. So at the end, I just want to understand what is the interpretation of not only the path integral, but also the numbers that we are computing in spin forms.
Okay. Good job. There are many things in your your question. It's not just one question, I think. So let me start from the end of what I was hearing, because you were saying, okay, in quantum field theory, this is different with respect to quantum field theory, because in quantum field theory, I really think in terms of you say the causal evolution. Obviously, here we are doing not even quantum gravity, but I would say gravity. And in gravity, what you mean by causal evolution is more complicated, in the sense that you don't have a preferred time variable. So this is not the problem of the amplitudes. This is understanding what you do when you work with gravity, and the fact that the evolution is always a relational evolution, okay? So I would separate the two problems. So first, solve the problem in GR, and the problem is solved. I mean, it's what emerged also from the discussion about the Wheeler-de Witt equation. The beginning was puzzling people because there was no time variable appearing, and now we have the evolution. We have the solution that is very simple. That you have simply to do a relational evolution. For instance, you can introduce a scalar field that works as a clock. Carlo, and then the other part of the question is what you do with these amplitudes, how you interpret them. I see, Carlo, you wanted to add.
Yes, you allow me to say one thing. The way I would think about this is the following. You said in quantum field theory, I think it's a causal evolution from the past to the future. Fine. But suppose you look at quantum field theory differently. You have some initial data, measurable, some final data, measurable, and there's some relation with this. Okay? They're not given, initial data don't get arbitrary causal data, or in quantum theory, some combination are more probable, some combination are less probable. Okay? So now forget the causal evolution. Just keep this in mind. Well, that's what is happening here. That's a proper way of thinking. The fact that you can do a causal evolution is specifically because you have a time variable, you can evolve in the time variable, blah, 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 blah. When you don't have that, you still have initial data and final data, which are classically some equations that tell you which combinations are possible, which are not possible. Quantum mechanics, which tell you which combinations are more probable, which combinations are less probable. So given some part of the data, you can say which other are more probable, less probable. I think that's a clean way of seeing evolution relativistically.
Thank you. Thank you. That was the interpretation of the probability was something that I wanted to clarify a little bit. Thank you.
More questions? Yeah. And I invite also not just Carlo, but also Mushin, because I am in an awkward position here in teaching this course, but then I have experts in the audience, so I invite them to interject questions in case. Yeah. So sorry, yeah, go ahead with your question.
Thanks. So every time I see like graphs or I see like something like a path integral, I think on renormalization. And I do think that there is some people working on renormalization for spin foams. But what is like being renormalized? Where like, I guess here there are no divergences because it's not like exactly Feynman renormalization. We don't have like it's not perturbative and it's background independent. But then what is being renormalized?
Okay. So I have a slide that has to do with this, but I don't know if I want to go into that. So let me add first. Let me start from some simple facts. So first of all, the theory is ultraviolet finite because yes, it's ultraviolet finite because all the quantities that you can compute have a very hard physical cutoff that is given by the minimal eigenvalue of these quantities. Like the area has a minimal value. You have a minimal area, you have a minimal volume, you have minimal angles, and so on. So, in fact, in a certain sense, quantum gravity, this kind of quantum gravity paired with quantum field theory provides a resolution of the infinities of quantum field theory because it tells that you cannot do an infinite, you cannot take things in the infinitely small. So very often in quantum field theory you have to introduce a cutoff, but here the cutoff is a physical one that the theory is offering you. This is in the ultraviolet. Then the peculiarity of quantum gravity is that while in quantum field theory you meet infinities in ultraviolet, here what we have are dangerous infinities in the infrared. So what could happen is that when you compute this transition amplitude in the bulk, and you have some finite region of your space-time, and you're summing over all possible spins, what could happen is that you can have like spikes, like some finite region in which, in fact, there is something like an infinite volume inside. So you don't want this to happen, obviously. And there is a lot of work in this direction, trying to understand better what happens. There are some very nice recent works that seems to indicate that when you have sufficient information of the boundary, so if the boundary data are sufficiently complete, this constrains the possible spins that you have in the bulk. And so the divergences are not produced. So again, a lot of work goes into study this, but then there is a very simple solution. So you study this to understand the theory, but the true real theory is a theory in which these divergences are not there, because we know in nature there is the cosmological constant, and this theory of quantum gravity has a formulation that I'm not explaining here, but Chao-Yin is gonna talk about this in detail in her lectures. The full definition of the theory is with a cosmological constant. And what the cosmological constant does for you is to provide a physical infrared cutoff. So, as I say, intuitively, the cosmological constant brings into the theory the information that the universe is finite. So if you can construct, I like to when I talk to philosophers, I like to present the theory as having the guidance from the fact that you want finiteness. The world is finite, or at least you as a physicist want to describe a theory that is finite, because otherwise it means you're not doing physics, you're not able to predict anything. So this means that from the beginning you have finiteness in the small and finiteness in the large. And so the cosmological constant, this infrared cutoff, does the job for you. And then I have more to say regarding renormalization, but it will come with some slides later. So I will take some more questions and then go back to this. Yeah. Oh, yeah. I mean, of course, for all the theory with the cosmological constant, Mushin is the expert, the leader.
Yeah, so I had a question about the path-in girls again. In general, in QFT, path-in girls are just, on a functional analytic level, completely like ill-defined and not usually like convergent. But in QFT, we don't really care about that. It's usually we take like the functional derivatives of it, and then we have various theorems that allow us to calculate your amplitudes. Right. So I guess the two-parter would be like, how do we make sure that in LQG our path integral is well-defined and also convergent?
Well, the fact that the amplitudes are finite comes with a beautiful theorem from 2009 that is due to Jonathan Engel. I don't see here, but he's here. And on the other hand, regarding the so first of all, even in quantum field theory, when you look at the expansion that you do in quantum field theory, it's not true that we know everything to the end of the expansion. So we just check few terms, and we look at the trend in this expansion. So if we see convergence in the few first terms, then we are happy. And the good thing in quantum field theory is that you do the computation, you extract the number, and then you check the experiments, and everything goes right. So then you're happy and you're confident. Of course, here it's more difficult because you cannot do the experiment and check that the first terms in your expansion are indeed right. So the idea is that you should do this by hand and check the first term and then go for the next term and then for the next term. And of course, the more you go to higher terms, the more vertices you have, the more things get complicated. So there are few works in which there are indications that things seems to go right, but I mean, you don't have a theorem at this point.
It could still blow up, no? Like, yeah, you don't know what is going to happen. Like, you could go to up to 100 loops or something, but it could still blow up.
Everything in life. We are physicists. Like we have also always the possibility. We have always to take into account the possibility that things go wrong in the end. But you work with what you have, and you see how far you can push it. And yeah, like in the case of quantum field theory, for the moment, it works very well. So suppose we make a computation for black holes and gives us a very nice answer, and then we check white holes in the sky, and then, well, okay, yes, maybe it blows, but I don't know, guys, Mushin and Carlo, you have something more to say regarding the blowing of the expansion.
The QED also has, in principle, infinite expansion, but we know it's an asymptotic series. So if you truncate, you get approximation to the nature up to how many digits. So yeah, usually we know how to deal with asymptotic expansion.
I think we should really be careful in separating the mathematical definition of the theory and what we have, what we want, the theory that is good enough to do computations. So for me, that's the most important part at this point. We have a theory that seems to be sufficiently well defined to do computations. So let's try to do that. More questions? So I have a new part, but is it, Mushin, a good time for the break? Or yeah, but I have a new topic, so I think it's better if maybe we do the break now, and then we start again after the break. Okay, thank you.